Okay, hello everyone. Welcome to Privacy, Data Quality, and More in Data Spaces. This is mainly around the findings of the Mosaic Run project, but it has useful things for many more than us. Mosaic Run is a precursor to the data spaces, and it provides useful concepts and Lego pieces that can be reused in data spaces or in your data markets. This concerns the entire data lifecycle from collection to disposal. The Mosaic system has its own type of architecture to create a data fabric that is able to spawn data market. But the tools cannot only be used at a specific point of the Mosaic workflow or in a data space concept. The tools can intervene at ingestion time, at filtering time, and at sharing time. Did I make you curious? Pierangela, coordinator, will introduce the issues at hand and how Mosaic Run has taken them up. Stefano Paraboski and Pierangela Samarati will talk about the protection tools able to filter and secure at several points. And Piero Bonatti will then talk about the policies that are used to augment the metadata, but also used to filter data. How does Mosaic Run transport data, link it to policy and tools? The project contributed significantly and to standardization, also a topic in the conference, by furthering evolution of RDF to make it compatible with very popular property graphs. Pierre-Antoine Champin will report what we did. Finally, Aidan O'Mahony will show how all this can be orchestrated in a use case to remove major roadblocks in use cases around intelligent connected vehicles, especially how to address GDPR and the like. And then we can discuss. So please leave your questions and comments in the chat, and I will channel them to the speakers. Pierangela.
Thank you. So let me share my screen. Can you see the screen fine?
Yes.
Okay, thank you. So as Rico said, the work we're going to present mainly the results from Mosaic Run, or Mosaico as we call him, that is aimed to provide ability for multi-owner data sharing for storage, computation, analytic, and integration in respect of confidentiality and owner control. So the starting point is, Rico mentioned before, data spaces, is that data produced all over the world are growing rapidly. And the world today relies on the availability and the possibility of sharing data and processing data. I think, the importance of data tracking, tracing, and everything that is in front of us from the COVID situation in response to the emergency. So from the tracing that we needed to the needed to analyze the information that was in front of us. And all the Rico mentioned before, data spaces for European data strategy, so for data spaces and the Green Deal. Problem is all the data-driven innovation and the benefits that we can have from the ability and of gathering data and for processing data, for understanding the data and introducing intelligence in the system can be hampered if you don't have the proper measures and technologies for providing protection over data. So it's not that providing protection over data is to diminish the possibilities of sharing data, but it's actually to make data sharing and processing even more possible for scenarios where the other choice would be no sharing data at all. So you do need to have technologies and solutions for properly protecting the data that you can then feed in your system and in your data spaces. So Mosaic Run's vision and goal is to enable data sharing and collaborative analytics in a scenario where you might have multiple, we call it data owner from a technical point of view, call it data controller from the GDPR, or data authorities. So you have different parties that can share data and can throw data in the market, and data can be analyzed with the full benefit of the availability of the information. So understanding the data and producing processing from the different data sources while enabling proper protection of the data. So what does it mean to enable proper protection of the data? Well, first of all, you don't have a single phrasing of protecting data. So you have different requirements that might come in, different need of protection for private information, for sensitive information, for company confidential information, for business tools. And putting your data in the data market for sharing and processing, you need to provide solutions for describing data, for understanding what the data are and how they can be assessed and used. And of course, you need to have not only way of phrasing what you would like to have, what kind of protections you would like to have on the data, but also enforcement technologies for making sure that the data are protected. So having technologies that can cover your data or can sanitize your data, meaning cleaning it from whatever is sensitive information, private information, or company confidential information. And of course, all this for real cases and real uses. And the case that Dana is going to talk about that Rico introduced before is for a real electronic vehicle scenario. So in Mosaic Crown, we look at this problem and we identify the different dimensions. We look at the scientific and technical challenges in front of us to provide such a privacy compliant data framework and management. And in framing the work, we distinguish different challenges and different aspects that we needed to look at. First of all, I mentioned before requirements capturing representation for the diversity of protection requirements from a privacy point of view, but also from security point of view, also for guaranteeing the integrity of the information, which needs to be correct, fresh, and complete. So you need to have ways to specify the different data protection needs and also the different needs for functionality that you might want to have over the data. So you need to have a higher layer of for enabling data authorities, or if you go one step back, data subjects and respondents, or if you want one step forward, needs from whomever needs information, whomever has the need to access data. So for policy regulating access, sharing, usage, and processing of data. And I mentioned before, is not only specification layer, because you can have a specification, but then at a certain point, you'll have to protect data. So you do need underlying technologies providing the technical means for actually having protection. So technologies that can wrap your data, can sanitize your data, cleaning it from sensitive information so that the data can be released and can be shared with others without compromising privacy. And all this, Rigo mentioned this before already, throughout the information lifecycle. So from when the data is gathered to where it is ingested in the market, where it's stored, and then when it is processed. So requirements capturing a representation, it means that you need to have the ability to attach to your data policies that regulates how data can be used, processed, shared, and also for secondary usage. And this means policies that need to follow data. And it's easy to say, but it's far from easy to come up with, and Pierre is going to talk more about it, to come up with expressive, efficiently computable, and comprehensive and easily usable approaches for specifying policies over the data. With respect to enforcing technologies, I mentioned before wrapping and sanitization. And here the distinction we made is wrapping as a way to cover your data and to cover whatever is sensitive or whatever cannot be seen by the counterpart, be it the storage market provider or the party to whom the data are released or the party who's processing the data. So to be able to cover the data so that the other party doesn't have a visibility of it. When you think about when you talk about wrapping, the easiest example is through encryption. Encryption that you can use for protecting data in storage, or encryption that you can use on the fly for protecting data in computation, for temporarily covering it as the data are processed for some part from non-fully trusted parties. And wrapping, which is reversible, meaning you can cover data, but then you can uncover it, so make the data understandable again to authorized parties, so it's reversible. You can go back to the plain text data. With respect to sanitization, which we distinguish as a technique that protects the data is in a non-reversible way, meaning you protect the data, and from there, if you do things properly, of course, you cannot go back to the original data. So example of sanitizations, would for instance, be even data truncation, so not publishing, for instance, phone number in the complete form, but a classical example is when you want to provide going towards the GDPR if data are sufficiently anonymized. For instance, if you want to anonymize data for release, if you want to produce aggregate or statistics in a privacy preserving way. So from the aggregate, you should be able to sanitize it in such a way that you cannot, observers or whomever receives the data cannot go back to the original data. So the privacy of your respondents, of your subjects, is properly protected. But still, you have computed average or statistical information that you can share and share with others. And then we mentioned before, all throughout the information lifecycle. So when the data, from when the data is born to where it's injected in the data market, when it is stored, of course, you need to worry also about the protection there. And you can have different assumptions from the data market. So the data market can be under the same control, so in the same trusted environment as the data authority, for instance, the data owner, if you have a single authority, or it might be not fully trusted, so you need to worry about confidentiality, or it might be not fully trustworthy, so you need to worry about integrity. And all these also for providing ability to process data and to perform analytics while doing this processing, not necessarily with complete visibility over the data. And here I mentioned before data owner. Actually, owner is from a technical point of view, we call it data owner, but is essentially what is there is the authority over the data. So what in the GDPR would be called data controller. And of course, you can think of these directions to go towards also data owner there, not be the data controller, but being the data subject itself. So towards the market where you can have also individuals contributing to the data market, like for instance, having incentive for sharing or selling between quotes their own information. So these aspects that I mentioned, these challenges that I mentioned, these dimensions are orthogonal, and they also elicit different investigations or different angles of the investigation. So policies for being able to express the requirements of protection or even of need of access to data, for enforcing measures, techniques in form of wrapping and sanitization, and then again all throughout the information life cycle. So, and the goal is there is if you can do this, and we hope, we believe and hope that Mosaico actually contributed to this vision. You can actually empower data owners with control on their data, so that you can actually enrich the possibility of sharing data. So protection, again, doesn't mean to prevent data sharing, doesn't mean to not having data sharing, but it means to be able to increase as much as you can data sharing opportunities in a privacy preserving way. So for improving on data protection, and then of course, if you have this with guarantees of proper protection, even the trust and confidence of citizens, of users, of whomever will be the data subjects behind those data sets, or even the data controller who has responsibilities, or the data controller or authorities that has itself some company confidential information in the data, or has to be subject to business rules, or has to be obeyed to privacy legislation and regulation. And then, of course, if you do this, you can improve value creation from data And as I mentioned already a couple of times, you can increase data opportunity and enable new data market opportunities. So this is for an introduction from my side, and then I will leave the floor to Stefano for starting talking about the techniques for enforcing protection in the data market. So thank you.
Thank you, Pierangela. Let me share my presentation. Okay, so as a technical aspect, so let's see what Mosaico has done in these areas. So I will briefly describe contributions and the work we did with respect with data sanitization and anonymization. As Pierangela said, the profile of these activities are represented by the application of transformations that are going to reduce and transforming in a reversible way the data. The motivation for the application of sanitization and anonymization is typically associated with the management of privacy requirements. And privacy obviously is a very complex topic. What is nice to do in doing technical work is to try to have a precise and technical definition of privacy. And thanks to the work of many researchers, Pierangela certainly had an important role here, we have today a number of techniques that can be used that are traditionally classified into two separate categories. On one side, we have matrix and privacy definitions that are typically called syntactic techniques, where you specify properties of the data that are released. And the classical example of these definitions with techniques is canonymity and diversity. On the other hand, you have approaches where you focus your attention on the structure of the query that you apply over the data. So the result that you want to obtain from the analysis of the data. So the focus is on the release mechanism. They are called the semantic approaches. And the classical example of those approaches is differential privacy. In general, so what's the typical motivation for the use of these techniques that anonymizing data, so protecting the privacy of data that describe properties, actions, facts about citizens, about individuals is extremely hard. No, simple approaches, unfortunately, do not work. And we have a number of examples that have been then provided by the work of researchers who were able to de-anonymize extensive data collections that we released. So in general, so simple approach, a basic approach that unfortunately we find also applied in many scenarios where you just drop the name or the identifier of the person, citizen, in most cases is not able to give you correct anonymization, because in most cases the data that you keep, that you make accessible, contain what are often are called POSI identifiers, so combination of attributes that are not able to identify 100% of the people, but may be used to identify a portion of the people whose sensitive data is published, and this is certainly a great risk and creates a great vulnerability. So classical example, if you consider the zip code and the date of birth of people for, depending on the granularity of zip code, but if you use a low granularity, a fine granularity zip code, a larger fraction of the population can actually be identified. So if you have a collection of data that contains sensitive information where the name or the ID was stripped, and you make this accessible, then a user may be successful in combining this sensitive data collection with some open data that describe zip and date of birth for a fraction of the users, and then doing a simple join, then you can do this re-identification, so essentially avoid the attempt at protecting this data quality. This is a classical example. Let's consider a scenario where you want to release medical data, and actually the pandemic, I think, really demonstrated the benefit that citizens can get from free access to large and precise data that describe, in a very detailed way how the pandemic has evolved, and that gives the opportunity to do a lot of scientific work, and also provide a good tool to make the user community really aware about what is happening. So this is a classical domain. So if you want to release medical data to support various types of analysis, you may have this idea that you drop the name, but you may keep the data of both and the zip, because they are significant, interesting to do some analysis about those data. But as I was saying, this may allow to make a join, recombine, and so essentially reconstruct the identity that is associated with some sensitive piece of information. So this problem can be managed using syntactic approaches, relying on what is called key anonymity. Key anonymity follows this principle. It's the idea that I can make data accessible that are sensitive by starting from typically dropping all the identifiers, and then classifying the information that is released, identifying what are the quasi identifiers, and then releasing the data under the requirement that the released data should be indistinguishably related to no less than a certain number K of people described in the data. You can do this keeping the structure of the data. Most cases we rely on relational models, so you release essentially tables, but the content, the tuples that are part internal to the tables are in a way decreased in information content by using generalization, by using suppression, so that all the data are each record is indistinguishable from at least K-1 other records. So like in this example, we can reduce the information content by using generalization and covering some pieces of information. So we may get, in this case, with K equal 2, so the original data is rewritten, reorganized, so that each subject is associated with at least a group of 2 of another subject. Still, this is quite interesting, is not sufficient alone to guarantee protection, because we may see in this example that the group of 2 patients that are described in the last 2 tuples are both associated with the same illness. So in this case, there is no actual protection of the sensitive information, that is the illness for a given person. So we have an evolution of key anonymity, an enrichment of key anonymity that is called L diversity, where in addition to the requirement that you release data in a way that guarantees that each sensitive piece of information is associated with at least K profiles, K descriptions of users, you also insert a requirement that you have to have at least L different values per each group of quasi identifiers. So in this case, this representation doesn't work. So you have to release the same data in a different structure, like the one that is presented here, that protects better the sensitive information. Okay, so that was the profile and the major properties of syntactic approaches with respect to semantic approaches. So approaches that are more focused on the technique, the algorithm that is used to extract information from the data, the approach, the technique that is most well known is differential privacy. The idea of differential privacy is that you have a mechanism that extracts some information from a collection of sensitive data, typically associated with citizens or people who have to be protected. And the guarantee that is provided is that the result of the application of the algorithm does not depend on the profile, on the properties of any single individual. So this is the idea. So actually, the formalization says that you have there is a bounded probability of indistinguishability, but in general, this property is enforced thanks to the addition of some noise in the original data. This gives so protection on the identity and the profile sensitive information about single individual. This is a quite powerful, a quite interesting technique. So certainly it's already used in some scenarios. Is quite delicate in its structure. We have different variants. For instance, one important classification is the distinction between local differential privacy and central differential privacy. With local differential privacy, you apply protection to every individual record, whereas for central differential privacy, you apply the noise to the result of the evaluation, and that typically gives you lower perturbation to the data, so better quality in the result, but also forces you to keep a stronger control on the data. In general, so these two approaches are both needed to support the requirements of real applications. In general, we can see that for syntactic approaches like anonymity and diversity, there is this important aspect that they capture better the real world requirements. So it's often we can find a way to express the kind of protection that anonymity and diversity provide in a way that is understandable and adaptable to many different domains. Whereas for the semantic approaches, it's not so easy to define the kind of protection that we want to achieve and how it works. So it's certainly more delicate in terms of the representation of what is the service that is provided. On the other hand, syntactic techniques may offer some exposure, some risk associated with the type of knowledge that the adversary may have that can be used to violate the protection, whereas for differential privacy, as long as we use it in the way that is specified, so exactly as a tool that is designed to be, then the kind of guarantees that it provides are actually quite strong, and that makes it quite interesting for the domains where it can work. In general, with a specific focus on what we did in Mosaico, in Mosaic Crown, we did work on both types of techniques, so both on syntactic and semantic approaches. Work we did on the syntactic approaches is the realization on scalable application of key anonymity and diversity on larger data collections using Apache Spark, so an architecture for managing large workloads using distribution, using cooperation among a number of distinct computational nodes. We did an implementation where we started from Mondia, which is one of the most well-known algorithms for the application of key anonymity and diversity. This algorithm is a greedy algorithm. The problem is well known to be NP hard if we want to optimize the configuration of protected data. So if we use a greedy algorithm that solves this potential problem, the algorithm is quite flexible, is able to manage both numerical and categorical attributes, and applies generalization, so in a way that is consistent with the requirements of the application. And so our implementation was built as an open source tool. It's available on GitHub, and it's also was designed to be easily adaptable, and actually our work was presented at the IEEE Percom conference this year and received the award as the best artifact, the best tool submitted to the conference. In terms of scalability, the use of Apache Spark gives us access to potentially quite powerful data processing architectures. We did an investigation about how the anonymization task can be adapted to and the Mondial can be adapted to the features of the Spark architecture. What we identified is the need in order to provide real scalability that there is some work that is done initially using sampling in order to reduce the computational workload and to identify then essentially in the first phase, the criteria that had to be followed in order to distribute the data to the many computational nodes that are used. And the scalability that we observed in our experiments is actually quite good. So if we have, let's say, 20 or 40 nodes, we actually are able to cut by 20 times or 40 times the response time for the completion of the anonymization task on these data collections. With respect to differential privacy, also, a lot of work has been done in this area. I just presented a single slide, describes the work done by colleagues at SAP, where the issue that was considered is how we can control the kind of exposure that can derive from the application of machine learning on a collection of data. The risk is what is called the membership inference attack, that from the machine learning model that is built with the training phase, it can be possible to extract some sensitive information about the data that have been used for training the model. So using differential privacy, we may reduce this risk. And this requires sophisticated approaches that have been produced in the project. So this is just to give just a basic idea about some of the work that we did on the project. Thanks. I think now it's your turn, Pierangela.
Yes. So back to me, just to quickly cover data wrapping. When I mentioned that for a guaranteeing protection, you need to have a way to express your protection requirements, and Pierre is going to talk about it, and then to have technical measures for enforcing it. And I mentioned sanitization, which Stefano went more deeply into it. For sanitizing, for removing from the information you release or store whatever is sensitive or private. And I mentioned data wrapping as a way to cover data for their storage or for covering them for processing against party not fully authorized. And we look at data wrapping or the application of data wrapping and the complications it was bringing in different contexts in Mosaic Crown. And I mentioned here too, one, data wrapping when you store data, and the other data wrapping on the fly when you need to do the computation. And data wrapping, I mentioned before, you cover data for forbidding their visibility, but is reversible, so you can open back data again. Now, the problem is when you use wrapping for storage, let's make it simple. Suppose that you simply use wrapping by encrypting data. Now, the problem is if your data are encrypted and they're stored in encrypted form in the data market, how do you perform computation? How do you run queries? How can the data market serve you if you yourself don't trust the data market for access data? So you need to provide way for having fine-grained retrieval from the data market when the data market itself is not fully trusted, because the information might be sensitive, might be financial information, healthcare information. The data market and the data market provider cannot see it. So here you can have encryption with support for query functionality or index-based support for query functionality. And they have actually similarities, meaning the strength or weakness that encryption with functionality or index have are pretty much similar. So what you need to have when you have indexes for supporting your queries, you need to make sure they're not exposed to inference. They need to provide effective and efficient for query evaluation. And of course, you cannot overload your client. The work should remain with the data market, even if you don't fully trust the storer. So different indexes might be more or less performing well with respect to serving your queries. Like if you have a one-to-one correspondence between the data and the index, you can serve well the evaluation of the quality conditions, but of course you're exposed to frequency attacks. So different indexes, they have different vulnerabilities. And what we did, we investigated the use of flattened indexing for providing from the whomever could observe the data, no information on the underlying plain text data behind. So flat indexing means that you cannot observe anything for the frequency, for the number of occurrences from your data. And the problem is that is not simple at all, because just let me cut the story short, because it is complicated, because you need to be then effective and efficient for query execution. So you can actually have a very strong index, but then if for performing a query where you need to retrieve 10 patients, you need to bring back home all the hospital database, it doesn't pay off. So you need to have an index that performs well, that doesn't give overhead to the client with respect to the storage that it has to maintain. And you can actually do that with flat occurrences. And the problem is complicated because you're not indexing against one attribute, the treatment, for instance, but you're indexing against the treatment, the illness, the doctor, the hospital, and so forth. So we studied approaches for producing indexing that could be privacy preserving and efficient for supporting query execution. The other flavor with which we study data wrapping is data wrapping on the fly for collaborative computation. And here the problem is you might have a single data owner or data authority storing data at different providers, or you might have different data owners, different data controllers. They want to merge their information for performing collaborative computation. I mentioned before the COVID situation. Nowadays we are in need to provide collaborative computations for data collected by the region, the hospital, the ministry, university for me, or employers for understanding what's going on in this emergency. But each of them will have some information they can share, plus some information they cannot share because it is private or company confidential. So the challenge here is to provide a way to have such a collaborative computation while not having the data controller completely share information with the other parties. And of course, even here, you might have pretty strong encryption solutions, but then they fall short, they don't scale in real life. Or you might try to do something different, which we tried even with respect to what do I need to maintain sensitive. So in conjunction with policy specification, where you can specify, for instance, who could view your data or who could process your data but not view them, and relying for can process but not view on the application of encryption on the fly. And the problem, just to cut the short, is complicated by the fact that query execution carries information and builds the baggage of information as it goes along. So for instance, if you want to find all the treatment and average premium from a join from the hospital dataset and the insurance dataset for people who had stroke, and the premium is above a certain amount, then you have different steps in the computation. But at every point in the computation, you will have a dataset that has been computed. Now, the information that the dataset carries is not only the data that are in the dataset, but it's also how the dataset has been computed. So if I have a condition, disease equal to stroke, and then the disease is thrown out, still is present as an information baggage in the relation. So you need to capture information content, looking not only at the attributes which are visible directly in the dataset, but also the ones that are implicit, like disease before, or also the ones that can be inferred because they are the result of some conditions that was at some point in the computation. So you need to look at the overall computation and to understand the information baggage that each of the nodes in the computation has. And then what you can have actually is, if you have different parties, you can try to allocate the computation in a privacy preserving way again to different parties, leveraging possibility of having wrapping on the fly to cover information they can't see. So for instance, if you have a task like this, a query like this, which is the one I had before, you can understand which are the different steps in the computation. And then if you had just to assign the computation, your availability of parties would be maybe limited to whomever is trusted fully to see the information. But if you can cover information as you go, then you can actually enjoy availability of more parties and maybe cheaper parties for you. So if you can understand the information baggage that is brought in each step of the computation, then you can assign to different parties their task, maybe possibly covering by dynamic wrapping information they cannot see, and then unwrap information back again when it can be seen. So here, wrapping with a different flavor, wrapping on the fly, wrapping dynamic, to enable involvement of parties that are not fully trusted in a controlled way. So in full respect of the privacy and in full respect actually of the policy, as I give the word to Piero, for which you're demanded to protect the data. And this with the benefit of performance and economic saving, because you can involve in the computation providers that might be cheaper, and moving this work a bit step forward, you can actually optimize any characteristic you like, as long as the party you would like to involve, because maybe it reduces carbon emission, or because it's cheaper, or because it is in a country different from where the data can be visible, because you know that you can rely on a dynamic wrapping for protecting the data for their computation. So I'll close here just not to take too much time from the next speaker, and I'll give the word back to Rigo and Piero. Thank you.
Thank you,
Yeah, thanks, Pierangela. Now we are getting serious, because when we talk about ingestion and treating data according to constraints and permissions that we collect at data collection time and give to data to make our data fabric intelligent, then we also need to talk about the expressiveness of such information. And here comes Piero, who has worked with me in the special project where we started off making new policy languages, overcoming limitations that we had in policy languages like P3P and do not track, and adapting it to modern world scenarios. And so thanks, Piero, for coming and giving us new insights from the follow-up from the special project, which is the Trapeze project, telling us where you are with the policy languages. So thanks, Piero.
I'm sorry, I can't hear you anymore. Something happened of being thrown out of...
We do hear you.
No, actually, we do hear you.
Oh, okay, great. Let me try to share the screen now. I hear you as well. Can you see my screen now?
Yes, everything's perfect now.
Okay, thank you. Sorry about this glitch. Okay, thank you for the introduction, Rigo, and thank you for the invitation to present our results here. These results are being developed within the project Trapeze. The policy I'm going to talk about today are data usage policies, and this is a broad term that is especially focused on the kind of requirements and protection that are related directly to the GDPR and that kind of data usage. So data user policies comprise privacy policies, the record of processing that must be kept by
I think when we have Piero back, I tell him to switch off his video and apologize for the inconvenience. But I think one of the disadvantages of ADSL is the A in ADSL, meaning Piero, can you switch off your video, because I think you will have upload issues.
Okay, let me try to stop the video. Everything is frozen here, unfortunately.
We see you again.
Rico was thinking as a fallback plan, we can show his slides and he can talk.
Yeah, I think we should go with Pierre-Antoine about those policies. Unfortunately, now you're missing a piece in the puzzle, because of course those policies use linked data. Piero, I think you're muted.
Okay, how is it now?
Yeah, now it's
great.
perfect.
So, very sorry about this.
Try to share your screen again. If it freezes, just send your slides to Pierangela, and then she will present, because it seems that is your upload stream. It is the upload stream. There is the bottleneck. Okay, so we'll wait until Piero is back. Hi, Piero. It doesn't work with your sharing capability because it kills your upload stream. Please give them to Pierangela, and we, in the meantime, Pierre-Antoine will start his presentation, and Piero, once Pierre-Antoine has finished, you can come back to us. Pierre-Antoine, okay. So in the Mosaico project, we not only did some nice architecture to create a data fabric that can be then used to create a data market for certain purposes, using sanitization to throw away things we don't want, use wrapping to secure things we want to have secured. But all of this is heavily relying on on semantic processing, meaning not only having data, but also metadata, the data about the data. And as this is all heavily standards driven, and we faced some limitations, the project started to invest into standardization. And I think this project was particularly successful in standardization, because we took the generic issue on how to create more interoperability between currently used formats, meaning we have JSON schema, we have property graphs, we have RDF, resource description framework, and so on. So Pierre-Antoine will talk about this and tell you about the challenges and the things we were able to do. So Pierre-Antoine will present. Please send your slides to Pierre-Angela, and she will then show them after Pierre-Antoine has finished, and then you can present correctly. Okay? So Pierre-Antoine.
Thanks, Rigo. Hi, everyone. So I will talk to you about RDF Star, which is an effort to bridge the gap between linked data and property graphs. So a quick reminder of what we're talking about here, linked data first. Linked data is a set of standard technologies for exchanging data on the web and to ensure an interoperability layer for other data models or data format. By interoperable, we mean syntactically, but also semantically interoperable. Those technologies, you might have heard of some of them. They are RDF, Sparkle, Shackle, and this list is not even exhaustive. We're speaking about W3C standards here. Here's an example of a very simple example of linked data. So it describes a car, which has a model name and a plate number, and this car is owned by a person named Jane Doe. So for this presentation, suffice to say that linked data is structured as a graph. And other graph data models have become very popular in the recent years, namely property graphs. So property graphs is not a data model, it's actually a family of very similar data models implemented in different systems. Well, the fact that it's not a single data model makes interoperability across those systems challenging. That's one of the acknowledged weak points of property graphs compared to linked data, which by definition are standards. But property graphs are nonetheless very popular because they represent a arguably more intuitive data model, as we will discuss on this example, and because the systems implementing them are very efficient when it comes to graph traversal or graph analytics. So this is the same example as before, the same information as before, representing the car owned by Jane Doe. There are a number of differences between the two approaches that could be discussed, but we will focus here on the similarities, and they are that both are graph data models. Objects of interest are represented by nodes in the graph, the car and the person in that case, and relationships are represented by edges in that graph. Okay, so up to this point, linked data successfully achieves its goal of being an interoperability layer between different data models, including property graphs, because as we saw, this property graph can be represented in a more or less similar linked data graph where objects of interest are nodes. There are other nodes in that examples, but objects of interest are still nodes, and relationships between them, the owner relationship, are still edges. Now, it becomes more tricky when we use another feature of property graphs, and that's properties on edges. Okay, nodes have properties, as we can see inside the boxes, but edges can also have properties, which allows us to represent complex relationships, such as the fact that Jane owns the car since a given date. And those complex relationships have been discussed for a long time in the linked data community, actually. There's a good practices notes on the W3C website dating from 2006 about so-called n-ary relations. And there are, in this good practice documentation, there are several approaches for representing this kind of complex relationship, but all of them basically involve introducing another node in order to be able to attach more information to that node. So, and this is sometimes perceived as overly complex. And what is usually disliked, well, often disliked, I mean, in some situations, this is perfectly acceptable, but in some situations, what is regretted is that the relationship is not anymore represented by a single edge between the car node and the person node here. And this is where RDF star enters. RDF star is a proposal to extend the data model behind linked data, which is RDF, to extend it with the ability to draw edges not only between nodes, but also between nodes and other edges. And so in RDF star, modeling the previous example with a complex relationship becomes possible just as simply as that. We draw an edge from this owner relationship towards another data. So RDF star has been here for a while. The initial proposal dates back to 2014 in a paper by Olaf Hartig and Brian Thompson. Sorry. And since then, it's been increasingly implemented by different open source and commercial products, to a point that we have today several implementations of RDF star that are not quite interoperable with each other, because this is not yet a standard, and because interpretations of the initial paper may vary, and also Olaf Hartig and Brian Thompson published further versions of the paper with slightly different proposals. So we have this heterogeneous landscape of implementations of RDF star, and to avoid too much heterogeneity and to improve interoperability, a community group in W3C created a community group report trying to stabilize what RDF star is or should be. Now, you may not be familiar with the W3C vocabularies and processes. So a community group is not a standardization group per se, it's much more open. But a community group report is not a standard, it's not endorsed officially by W3C, but it's published with a similar license as standards, which means that it can be implemented safely without risking to infringe patents or things like that. And actually, this report has been implemented already by, so a few of the existing implementation have been adapted to comply with that report. The next step, and we are in the middle of this at the moment, is to turn this into a proper working group, which is a group with the power of publishing recommendations, so proper standards. So let's say that we have a stable specification for RDF star, and a standard is hopefully on its way. So mission complete. We have a straightforward way to go from property graphs to linked data and back, right? Well, not quite so. We have a way, we have building blocks for doing that, but the devil's in the detail. And many newcomers to RDF star have hit a number of caveats and pain points that I want to explain here, just to show that, well, although we have bridged the gap to some extent, there are some fundamental differences between property graph and linked data, which, and so people must be careful with what they're doing with RDF star. The first pain point is this kind of pattern, which is very common in property graphs. So here we still have our car, we still have its owner Jane Doe, its current owner since 2019, but we also represent the previous owner with another edge owner with a start and an end date, okay? And this goes to show that the semantics, the meaning of edges in property graphs can be contextual. It can depend on other things, in that case, on the properties on the edges themselves. I say it depends because the lower edge represents the current owner and the upper edge represents the previous owner. Those are not exactly the same things. It's not exactly the same meaning. Now, we can still do that in RDF star, can't we? Well, we can, but then we would not accurately convey the meaning of the previous property graph, because in linked data, remember that linked data was designed for the web, and the web is an open world, okay? In linked data, you cannot rely on the context to interpret the meaning of edges. Otherwise, since you are never sure that you have the whole picture, because the web is an open world, you would never be able to draw any meaning from any arc. So this would actually mean that the relationship between the car and John and between the car and Jane are the same relationship, which is not the case. Okay. Fortunately, we can circumvent this problem with RDF star, because we don't have to include the edge between car and John in our graph. We can use that edge as the starting point of other edges from and until, without actually endorsing it in our graph, or without asserting it. That's a subtle difference, okay? And what is tricky is that this distinction was not present explicitly in the starting property graph. Here we had to make explicit some semantics that was only implicit in the property graph. And that's very good for in the property graph world, okay, to keep the semantics implicit and to implement it directly in applications. But linked data, by definition, needs to make the semantics explicit. And so the transition from property graph to linked data requires that extra effort and is not as straightforward as some people might think. Another pain point is this ability that some property graph systems have to have multiple edges between the same nodes with the same label owner. So this is used to represent that John Smith owned the car actually during 2 different periods of time. So apparently he owned the car from 2015 to 2016, then sold it or gave it to someone else and bought it back or took it back in 2017, okay? What if we try to represent this naively in RDF star? An important thing is that in RDF and in RDF star, edges can only exist once. And that's related to the fact that edges represent assertions, okay? They represent the fact that this car is owned by this person. This is either true or false. This cannot be true twice or 3 times. So edges in RDF are unique. And if we collapse all this metadata about the ownership into a single edge, then we lose information because we can't know anymore which start date goes with which end date. So in order to correctly convey that information, one solution is to introduce again nodes to represent the relationships. Okay, so we have 2 occurrences of this ownership of the car by John Smith, one from a given date to another date, and the other with different dates. This is a bit surprising to a number of people coming to RDF star. This actually has been discussed a lot in our community group. Not everyone is happy with that, but the general consensus is that we don't have a better trade-off between ease of use and the inner the way RDF star is designed. So to conclude, RDF star reduces the impedance mismatch between linked data and property graph. It doesn't eliminate it completely, as I just showed. All this is not cast in stone. As I said, this is for the moment a community group report, not a standard yet. The working group will be able to revise a few choices that we have made. And so if you want to weigh in, if you're interested in this, we are eager to get more feedback and more use cases. And anyway, we want the future standard to be useful to as many people as possible. So feel free to join the community group or the future working group. And that's all for me. Thank you.
Okay, here we are back. Thanks, Pierre-Antoine. This is very interesting because one of the things I know is that the property graphs are much closer to the way the human brain functions or humans think, because they put loads of properties on edges, and that's easier to think than. So, Piero, should we try again?
Yes, please. Let's try again and see how it works this time with the help of Pierangela.
Yes. Okay. So now we have the...
Okay, I've changed the operating system, so I might as well try to run them myself, but let's try to minimize the risk.
Yeah, okay, no, run it.
No,
for
let's use Pierangela's. Let's use Pierangela's help just to minimize the risk.
Okay,
so
then you say just next slide.
Yeah, let's move to the next slide because the first one has already been discussed. So let's resume the conversation. Data usage policies are that kind of policies that are more closely related to the GDPR. They cover privacy policies, the record of processing that must be kept by controllers, the consent of the data subjects, and the GDPR, which is itself a sort of a high-level policy that talks maybe about purposes in general, about categories of special data in general, whereas the other policy talk about concrete sensitive data or concrete purposes. But more or less, the information is the same, although at a different granularity. Now, complying with the GDPR requires many things, and among these things, it requires that the privacy policies should satisfy the restrictions placed by the GDPR on data transfers, on the processing of sensitive data, and so on and so forth. And the personal data processing should comply with also with consent and maybe lack of consent from the data subjects, where consent changes dynamically. So given the very large volume of personal data that are being processed in data markets, but not only there, and given the dynamic nature of consent, it is of paramount importance to automate compliance checking and policy management, because otherwise being compliant become unfeasible. And in turn, this requirement implies that policies should be machine understandable. Please, next slide. Now, there is a list. This is a list of use cases that we are trying to automate. The first one is the validation of a privacy policy with respect to the GDPR. This must be done before deployment and is of interest to controllers. The second use case is auditing, monitoring these policies. It's a sort of an ex post compliance check carried by the data protection authorities, the data subjects, in order to monitor what the controllers are doing with personal data. Then we have access control, of course, which is meant to check dynamically whether the operation being currently executed complies with the privacy policy and consent. And we have challenging examples in terms of performance coming from our industrial partners, who are some of which are telecommunication providers. Now, while reasoning about access control, we realized that an approach based on checking operations one by one is not necessarily working. In some cases, it doesn't. Because consider an entire business line doing different a sequence of operations on personal data. And suppose that in the middle of this sequence, you realize that the next operation is not allowed. So you have to stop it, to abort it in the middle. And for that reason, all the operations you have done so far are useless. You throw away, hopefully throw away the results, but you might have results that remain persistent in your system. And this is unlawful because the GDPR says that processing must be necessary. So this turned out our attention to a full ex-ante compliance checking. That before feeding a piece of personal data into a complex business line, checks in advance whether the entire set of operations that the business line wants to make is compatible with the consent of the data subject. Last but not least, of course, we are implementing facilities for explaining the results of compliance check. A sample question that might be of interest for... No, wait a minute, sorry. Back, please. Thank you. A sample question for coming from the controllers could be, why is this privacy policy not compliant with the GDPR? While a simple question coming from a data subject could be, why could the controller use my data in this way? Thank you. Next slide, please. So the solution of Trapeze is using one simple language to express all data usage policies in a uniform way. So privacy policies, consent, and the objective part of the GDPR. And provide alternative syntax to make things more usable. So we provide JSON, ODRL, and OAuth2. The properties of this solution is that it is usable from the point of view of controllers, citizens, and also the developers. It is reliable. We can mathematically prove that our tools return no false positives and no false negatives. It is also interoperable through the use of standard formats like the above and also ontologies. And ontologies are also the way to make it extensible, following the evolution of the regulation and the new domains, sending everything to new domains. Last but not least, it is scalable. We can, with a simple implementation, I will talk about that later, we can scale to 1,000 compliance checks per second. Next slide, please. So this is an example of how a policy would look like using the JSON language. It is more or less like a form, which makes policies so usable. So we have different properties: the purpose of the processing, which in this case is marketing, the data categories that are being processed, so demographic data, location data. The result of the processing are disclosed to a company called Acme, and the nature of the processing is a kind of automated decision-making with human involvement. Okay. Now, since this is a sample privacy policy, it would go on with further properties, specifying what is the legal basis for the processing, possible obligation, to which protection measure are used, and information about the storage, such as where are data stored and for how long. If these were a consent policy instead, the structure would be the same, but the properties would be slightly different. Maybe again, information about the storage, but also which controller is this consent given to, possibly a sticky policy specifying restriction on how it can be further, data can be further disclosed to third parties. Next slide, please. And this, when you have a complicated privacy policy, maybe you want to have many of policies like in the previous slide. So you get a policy set where each element in the set may focus on a different purpose or a different data categories, maybe both. And this set of policies is explicitly linked to a set of ontologies that specify the meaning of the terms that are used in the policies. So you have a self-contained object that contains its own meaning. It can be shared with other software agents. Next slide, please. And with the same language, you can also represent the GDPR. In this case, the set of policies represents the set of articles and paragraphs of the regulation. Next slide. So, for instance, these policies or norms could be inspired by Article 45 that says that information can be transferred based on Article 45.3 to a country for which the European Union has issued an adequacy decision. And here, for example, we use this class of countries, EU-like, to denote exactly these countries that have an adequacy decision. Or alternatively, in the middle, we have Article 46.2a that says that information can be transferred to other arbitrary third countries if there are sufficient technical organizational measure, in this case, a legal agreement between public bodies. And in this case, also a legal basis is different. And then you can go on like this, enumerating all the norms of the regulation. Next slide, please. Okay. The beauty of this approach is that this language is vocabulary neutral, which means that the property names used in the policy, the classes used as the values of those property names, are not hardwired in the language. They are defined in the linked ontologies. So, for example, Trapeze is now adopting the vocabularies developed by the Data Privacy, Vocabularies and Controls Community Group of the World Wide Web Consortium, in which also Rigo is involved. But in the future, they could be replaced, refined, extended by changing the ontology without affecting a single line of code in the machinery, in the tools that we are developing. So the code of the compliance checker would remain untouched, same for the explanation facilities, and their correctness and scalability will still be guaranteed. Next slide, please. Here is an example of what it means to extend the vocabulary. It's very simple. This example is inspired by the case of South Korea that currently doesn't have an adequacy decision, but the process of creating this adequacy decision is going on now, and it will end at some point. If the outcome will be positive, then it will be necessary to add a new name, South Korea, with the first blue line, and say that it is one of those EU-like countries with an adequacy decision with the second line. And automatically all the system will adapt and start treating South Korea as a place where information can be transferred without any particular measure. Next slide, please. Now, JSON and ODRL are familiar to developers and companies, but they have no formal meaning. You pick two random participants to a standardization activity, they will use the same format in different ways, almost surely. They will give different meanings to each piece of the format. So this does not allow interoperability. For the reason we translate the JSON and ODRL, the external formats, into AU2, used as an internal format, because AU2 has a mathematically sharp meaning. And next slide, please. This formal semantics makes it possible to let all stakeholders and software agents understand the policies in the same way. And it's also what is needed to give the strong correctness guarantees on compliance and explanation algorithms, so that they return no false positives and no false negatives. And it also guarantees that all these algorithms for the different tasks return coherent results. It's never the case that one says the policy is not compliant and the other one says that it is. Next slide, please. Now, we are continuously assessing whether we are meeting the objective that I listed in the beginning. So we already know that controller employees can formalize the privacy policies of their employer using our language, of course, with the suitable graphic user interface that show the policy as the forms that they really are. And this proves both the usability of the language and its expressiveness, because it proved to be adequate to encode some of the most complicated privacy policy we have seen. Second, developers can use policy formats and understand compliance checking. Our partners, who are not theoreticians, have already re-implemented the compliance checker as a smart contract in a blockchain, as JavaScript code. There are no dependencies on complicated and possibly proprietary black box technology. And then we also are confident that compliance checking and explanations are very scalable despite AU2. It is possible to do everything very fast using specialized algorithms. We can carry out a compliance check in about half a millisecond. And we are extending the language with individuals, overriding and recursive sticky policies in a way that will keep this same performance. And I stop here. Sorry for all the trouble and for causing some delay.
Yeah, because of the delay, we are very close to 17:30, where we were supposed to stop, but because of the glitch, we are a bit late. I invite everyone who remains interested to follow, because now Aidan O'Mahony from Dell EMC in Cork will tell us how you can take all the insights that we've gone through now. How do we transform that into a real world use case where you can have fleet management and really much higher convenience and personalization while remaining GDPR compliant in a use case around intelligent vehicles. And as Piero has already said, and as others have shown, this is not easy, but it's feasible. We'll continue, and we'll have already one question for after Aidan has finished. Please stay tuned. We'll finish, I think, around 15 minutes late. Aidan, please.
Yeah, thanks, Rigo. My slides are up okay, are they?
Yes, they are.
Brilliant. Thanks very much. I'd like to introduce use case one, which was the intelligent connected vehicle use case, and how we were able to leverage the tools and techniques that were delivered as part of the project to actually implement and take advantage of this use case. So use case one involves a fleet of intelligent connected vehicles and a charging station infrastructure within a city. So we developed this use case in conjunction with Jaguar Land Rover, and really what we wanted to be able to facilitate is the sharing of private data in such a way that both parties would be able to gain some beneficial insights into how the various pieces of equipment or whatever are actually taken advantage of. So for example, in the charging station infrastructure providers case, they might want to gain insights into how the charging stations are being used to see if there's some are being utilized more than others. And in the case of the fleet owner, they might want to be able to see how their fleet is being used. However, we also had the consideration where the drivers of the car might not want their data to be shared. So we developed this use case, and we were primarily concerned with the ingestion phase of the data lifecycle. So that's the application of policy, of data wrapping and data sanitization as it comes into the data market. And from that, then we also wanted to facilitate various forms of analytics. These could be analytics that are carried out within the data market, as you can see on the bottom right of the screen, or these could be facilitating access to the data itself, where the customers of the data market could carry out the analytics outside of the data market. So just to give you a bit of a flavor for what we developed in the end. So we've developed this data market where, as I mentioned, the fleet owner, the infrastructure provider can come and gain the insights based on the behavior of the drivers of the vehicles. So for example, on the bottom, on the right-hand side of the screen, we can see a heat map of Cork in Ireland. We can see the charging stations. We can see the utilization in the heat map. We can see which ones are offline, online. On the left-hand side, then we can see the vehicles themselves, the colored dots. And as the cars travel around Cork City, then we can see as they go to charging stations, and we can see their destinations, we can see the behavior and the status of the car. So these are the types of insights that are available to the customers of the data market that we developed. As well as that, then there's also the option to access the private data, but of course, what we have developed then is the facility for the data owners to maintain control over how that data is actually accessed, how it's treated, what use or for what purpose the data is accessed for. So this is really what we developed as part of use case 1. So the interface for the driver really is we developed a simple Android Auto application which allows the data owner, the car driver, to be able to select policies based on how they want their data to be treated. So one of the requirements we had then was to develop a model for licensing or for economizing or being able to monetize the personal data, and we developed the application with this idea of charging station tariffs in mind. So based on how the data owner wants their data to be treated, they can actually get discounts on the electricity in the charging station. So the API that was provided to us to access data from the cars returns data in a straightforward JSON format. So an example of this data is here on the screen. And as you can see, the data itself is straightforward to understand. However, you can immediately see how there might be difficulties in using this data in such a way that the privacy can be preserved and policy can be applied to it. So one of the issues we had was being able to take this data and transform it in such a way that it can be used in a semantic context. And as well as that, part of the work that was done in Mosaic Crown was the development of the policy language. So we needed our data to be interoperable and to be able to link together with the policies that the driver of the car or the owner of the fleet or the charging infrastructure provider, so the policies that they define and how the data should be treated. We needed the data being ingested from the car to be able to interoperate with these policies. So that was one of the challenges that we had as part of the project. So what I present on this screen then really is what we developed over the 3 years. So what we have now is a end-to-end data market where the vehicles can ingest their data and they can supply policy, how they want their data to be treated. And what I'll do now is I will describe from the top center in a clockwise fashion how this data goes from, or how it flows from the vehicle all the way to the far left, which is where the customer of the data market, the customer of the data market actually interacts with the data. So we have the two situations where the Android Auto can supply data and can supply personal data from the car. We also have generated data for the electric vehicle charging stations. All of this data gets ingested into a central point, which we call a message broker. So our message broker is built upon a number of open source tools, which we've taken and modified as necessary. And it takes in the data, it then transforms it such that it has semantic meaning or gets semantified. One of the decisions we also made at an early stage was to split the data from the metadata. So the metadata gets stored within our knowledge graph, gets converted to RDF, and then our data, which we defined really as data that's very rapidly changing. So this might be, for example, location information, or it might be speed. So this is data we treat or we store differently to the metadata, and we store this data inside a standard object store. The message broker then, as I mentioned, will transform the data. It'll also take in policy information, which is already in a format which we can easily store. And once it gets transformed and converted into a suitable format, it gets stored in an intermediate destination, a data lake. And from the data lake, we consider the data as flowing throughout the system. So from the data lake, it'll flow into the data market filter. Now, the data market filter will determine how we want our data to be treated. So we took advantage of some of the tools developed part of the project to create this data wrapping component, which takes the encrypted file system and the novel all or nothing transform that was developed, and the data as it flows through our system then gets either it can get wrapped, or it can get sanitized, or it can flow straight through depending on the wishes of the data owner. So again, this comes down to how the data owner has stipulated they want their data to be treated. So from the data wrapping and sanitization stage, our data then flows into the data market, where it's ready to be served up to customers who come to our data market. From the far left, we developed a user interface which customers can interact with. They can log into, new users can be created, and it's from this perspective then that the users access the private data in the data market. And this data market then is really buffered, or it's controlled by a policy engine, which was also developed as part of the project, and we integrated into our platform. So if you can imagine a scenario where a electric vehicle charging infrastructure provider wants to access specific data belonging to a data owner, but they want to use it for some purpose that the data owner has not given access to. So again, it's the policy engine then that will control access to this data. So it'll either grant or deny access based on the purpose of the request, or who's requesting this data. And again, the user will be able to stipulate that for certain data they're happy, for example, for it to be used for advertising purposes, or perhaps they don't wish that, or they can say for certain data we don't want it to be shared with users that are in certain geographies. Or again, the Mosaic Crown policy language is very expressive, and it allows the data owners significant control over their data. So this is the overall data market that we developed as part of the project. And again, we're able to show data being controlled or being deleted, or if a user changes their policy during a journey, for example, that gets reflected in the web UI and the access to the personal data. So using a number of the components that were developed separately outside of Dell, but as part of the project, we were able to develop this platform. So again, on this screen, we just show a brief example of what the data looks like inside in the data market. Again, we can see how the vehicles get linked to the metadata, gets linked to the data, gets linked to the policy. And again, a lot of the work really was in determining how this structure should be created and how the data should be accessed, how it should be stored, how the policies should get stored, and the various transformations and treatments that were required to satisfy the policies of the driver. And just to make a comment on RDF Star, which was presented earlier in this session, RDF Star was developed relatively recently in the project. However, we can already see, I think, pretty useful and immediate benefits if the project was to continue. I think we could definitely have integrated RDF Star into the ICV use case. And just an example here, I show how RDF Star could be annotated, how our data could be annotated to, for example, indicate that at a certain speed, our driver may not want this information to be used for certain purposes. So, for example, if our driver is somebody who perhaps doesn't like to obey the speed limit, they can specify that in their policy that for certain purposes they don't want that particular data to be used. So again, we can already see that RDF Star could be of benefit to the ICV use case and use case 1. So as I'm already over time, I think I'll hand back to Rigo. I do have other slides. If there's questions later, I can probably refer to those. So Rigo, I'll hand back to you.
Yeah, so because we are already over time, we have little time for questions, but in the chat, we already got one question, and this one goes to Stefano from Christos. I would like to ask if federal machine learning can be considered a solution to problems that have been reported, such as data security, availability, and if a federated machine learning technology has the potential to bring about significant changes in the areas of health, fintech, banking, and more, which reminds me that those are not exclusive to what we are talking about here, because in an earlier presentation around 1500, we talked about data quality and liability for machine learning if you use bad data quality in your machine learning. So, but Stefano, Rampy.
Yeah, no, just a few observations. I think federated machine learning has an important role, and actually is one of the motivations of the work we did in Mosaico. It was mostly a partner SAP who did work in this area, and the idea is that federated machine learning certainly can support security and data protection requirements and privacy requirements in an interesting way. Every time you have to do that type of analysis. Obviously, machine learning is quite important. That doesn't cover all of the applications where you have to use the data that has to respect the privacy requirements. So for on that sense, so the realization of federated machine learning is fully compatible with the idea that you have a market, a data market. And today, if we look at the strategy for European strategy for data with the idea of data spaces, that also fits, because even if you, in a way, want to apply machine learning in a federated way with contribution by different parties, you still want to have a single actor who is responsible to establish a connection and cooperation with the other parties. So this is the depiction at the start by Pierangela, I think is compatible with this. In general, in terms, considering my presentation about what can fit well with the requirements of federated machine learning, I certainly see the application of differential privacy as most adequate for that scenario, compared to, for instance, to the use of syntactic approaches. So and in general, the first slide we represented work done in Mosaico, where there was this idea that you can use differential privacy to verify that there is no leakage about the potentially confidential content that was used to train the model, is actually a good technique that can work in many domains. Certainly, there is a lot of work to do. So it's an area with a big potential, certainly requires an integration of expertise and skills on both machine learning and security, and probably there are not so many researchers that are able not to put together these two expertises, and so there is certainly a big opportunity in working in that area, opportunity in terms of research impact, and also opportunity in terms of long-term impact on solutions. It's so an important element. Still, there are, I think, a lot of issues that have still to be covered. For instance, there is, I think, the models that I saw that I know typically consider a model where typically the parties that contributed to the construction of this federated model are typically expected to be trusted, in a way, so not to contribute a potentially dangerous or malicious model. I think my experience in working on research is that that type of consideration, that limited trust in the cooperation. So when you build a system where you put together results contributed by multiple parties, where you have the possibility that some of them are malicious, really has a big impact on the kind of techniques that are able to work. And I think that's, for instance, an area where I'm not aware of important results. Where certainly there is a lot of work to do. I hope. Okay.
Yeah, thanks. Yeah, we already talked about also that those nodes for multi-party computation would then, using linked data, expose the policies and capabilities that are provided by such a node to multi-party computation, and I think those techniques can be combined. But I want, because we are over time, but still 5 minutes early to the announced extension, I want to thank everybody, the speakers. I think this was a very good and informative session. I want to thank every speakers. I want to apologize again for the glitch with Piero, perhaps to bandwidth and update Ubuntu issues. I suffer from them regularly, and so thanks everybody, and thanks, and have a nice evening, and have a nice remaining EBDVF 2021.
Thank you.
Thank you.
Thanks. Bye-bye.
Bye.
Bye, everyone.
Recording stopped.
Okay.
So many thanks to you all.
Okay, worked.
So nobody's listening to us anymore, right?